Welcome back my dear friends, a very good morning, good afternoon, good evening to all of you wherever you are in this part of the globe. And this is the DADM 3 which is Data Analysis and Decision Making 3 course under the NPTEL MOOC series. And as you know, this course total duration is spread over 12 weeks and the total contact hours is 30 hours, which when broken down into number of lectures is 60, because each lecture is for half an hour and in each week you have 5 lectures and after each week you have an assignment. So, if you can see, we are in the 37th lecture, which is the 8th week. So, you have already completed 7 assignments and in totality you will have 12 assignments. After that you will take the final examination. So, if you remember, we were discussing about the DA method. I told you about the background, what are the DMUs, what are the input bundles, output bundles and how many DMUs are there, why this DA method is utilized, considering there would be many subjectivity concept also being brought into the picture. And in this problem formulation, if you remember, I said that we will try to consider the inputs and outputs and then try to formulate an efficiency score and then find out the ranking. But in doing so, I also gave you 3 scenarios under which you will try to do that. One is the decreasing return to scale, next will be increasing return to scale, another will be the constant return to scale. In the decreasing return to scale, increasing return to scale and constant return to scale, per unit increase in the input would basically bring down your profit per unit. In the case of decreasing, it will increase per unit. For each additional inputs, your output will increase per unit stage by stage, and in the constant return to scale it will remain constant. So, which means the rate of change of the functional form in decreasing would be increasing at a decreasing rate in the and in the case of the increasing return to scale, it will be increasing, but increasing at an increasing rate, and in the constant return to scale it will be increasing at a constant rate. So, obviously, if the first derivative's properties are known to you, you can basically talk about the second derivative properties for the decreasing, increasing and the constant return to scale. Now, in the decreasing return to scale, I drew 2 graphs, when in one case the x axis had the bundle of inputs, y axis had the bundle of outputs, and there it was shown that any DMU trying to move to the, if it is an inefficient, trying to move to the efficient frontier would basically move vertically up, considering inputs are fixed and you are trying to increase the output. It can move horizontally to the left such that the outputs are fixed, but inputs are being decreased. And then the other thing is would be it can move in a tangential direction with respect to the curve, which is the efficient frontier, such that it will decrease in input and increase in output in some proportions depending on which direction it is moving and how it can basically touch the efficient frontier, considering the shortest distance would be the tangent point. Now, I am coming to the increasing return to scale. So, the analysis would go in the same logic. First, we will consider in the x axis the input bundle of goods, then in the y axis I will consider the output bundle of goods, and then reverse the discussion, where the x axis would be the output bundle, the y axis would be the input bundle. Try to analyze that and then in the similar way go for the constant return to scale. So, considering this diagram, I would be using the highlighter in order to specify that. So, here you have the graph and your inputs are given in the x axis, outputs are given on the y axis. The suffix e, where the pointer is pointing, whether output or considering to the input, we will consider as an efficient, the subscript being for the efficient one, and any other subscript like 1 1 1 2 r would basically denote the position. So, if the DMU 1 is inefficient, similarly DMU 2 is also inefficient, but we are not going to draw the movements of DMU 2, only will highlight that for DMU 1, and basically that can be done for DMU 2 also. So, in the DMU 1, If this is inefficient, then it can basically reach the efficient frontier. Considering the increasing return to scale, it can move in 3 ways. One is vertically up, which means the input bundle remains same, output increases, and this vertical up is the pink line. So, it becomes the pink color scheme is there in order to make you understand. So, the pink one DMU 1 would be the efficient one, considering is an input oriented. Another thing which I did not discuss in the last lecture was basically the subscript I/P, which is basically trying to denote that is the input oriented model. So, input oriented model, I will come to that why, and it is very logical. So, in the input oriented model, what you are doing is that the inputs are technically fixed, you are increasing the output at the same level of input. Now, if the DMU 1 moves on to the horizontal left point, which is the blue line, it comes to the efficient frontier, which is this black point. So, this is the blue one, which is DMU 1 suffix in efficient, and this is blue in color. Let me show you why it is blue in color. This will. So, this is blue in color. So, it means that is the output oriented model, where the output is basically fixed and you are trying to basically decrease the input. And if it moves radially, obviously the radial movement may not have been drawn very absolutely perfectly, but you will get the information that if it moves tangentially and it is tangent to this point when the 90 degree is, as it is being denoted here. So, obviously what it will mean that the inputs have decreased by this amount, and obviously the outputs were here. So, they have, so inputs is decreasing, and let me so here in this direction the input is decreasing, and in this direction the output is basically increasing. So, output was here OP1 to this. So, output is increasing. So, you both basically have both of them, as in the decreasing return to scale you had input decreasing, output increasing in some proportions depending in which direction moving in the tangential green one. Here also the DMU, so this is increasing here, this is what I meant, this jump is the increase of the input, and this decrease, oh sorry, the yellow, this should be the green line. So, this is the decrease in the input. So, now obviously one point which I will try to highlight once I finish the decreasing and then do consider the increasing return to scales, the last diagram. So, I will come to that by considering all the 4 diagrams at one go. So, in this case again I am repeating, vertically movement up is input same, output increasing, horizontal left input decreasing, output fixed, and radial movement in some tangential direction such as tangent at the curve would basically mean some proportional decrease in input and proportional increase in the output. So, the word proportion which I am using, that will come out very easily through a diagram or using very simple trigonometry. I am going to come to that. Now, when I consider the increasing return to scales, so considering the input is along the y axis, output along the x axis, and you have DMU 3 which is efficient. So, we are not going to consider that. DMU 2 is inefficient, it can also move, but I am not going to draw diagrams for that. I am only consider DMU 1, which is the black dot here. DMU 1 is inefficient, it can move either vertically up, horizontally left, and radially. So, radial point is basically it is going to touch the curve in such a way it is 90 degrees. So, in that case when I consider the increasing return to scale, it will mean this. So, here it would mean that I am able to increase the inputs and increase the outputs also. Similarly, this curve would also imply that for the same level of input. So, I am trying to basically, so the points would have been on this side, my mistake. So, they basically they are here. So, any movement in the direction where they move would basically imply that the inputs and outputs are increasing or decreasing proportional to the case for the increasing return to scale. So, what I meant for the trigonometry would be very nicely explained by the first diagram. Yes. So, this is the diagram which we considered in the last lecture, which was the first lecture in the 8th week. Now, consider why we are trying to do that. I will come to the optimization problem later on, why we are doing this. Now, consider DME1 is inefficient. So, if it moves vertically up, so it is efficient here. So, I draw the diagram. I will use the green color here, or I can use another color, wait. So, it will be easier for us to. So, this is efficient. This point which is moves horizontally to the left, this is efficient, and the curve is like this. So, obviously, a nonlinear curve is made out of small linear points. Now, consider there are no more points in between. So, there are no more efficient points, but I want to find out that how DME1 can move in the radial direction. So, what I will do technically is join these two points. So, now it is a triangle. So, triangle I will mention is as A, B and C. So, if the point C wants to touch the line AB, it will move in that proportion such that it is tangent. So, this is 90 degrees, and if we use the concept of congruency and triangle properties. So, the proportional movement in the direction, if a decrease in input is happening, an increase in the output would also happen from the point C. So, consider this line is now the efficient one, because I have not been able to draw the curve considering there is only 2 points A and B, there are no more points in between A and B. So, consider this is C dash. So, if C wants to become C dash, there has to be an increase in the output, decrease in the input. So, the proportional increase and decrease in the output and the input would be happening. So, this would be the proportional increase in the output, this would be the proportional decrease in the input, and using concept of triangle and congruency you can find out what would be the ratios, and you can basically find it out. So, if A, B are such that C dash is in between middle point, then the proportional concept can be found out very easily. It can be done for other ratios also, you can do that. So, this you can do it for the decreasing one and the increasing one return to scales also. Now, coming to the constant return to scale, in this case we will have only one diagram, because the constant return to scale, the diagram would be such whether you consider the inputs along the x axis or outputs along the x axis, the line would be a straight line considering the rate of change of the functional form is happening at this constant rate. So, dy dx increases at in constant rate. So, if I have any DMU which is inefficient, so it can move vertically up the blue line, it can move horizontally left, which is the pink line. So, vertically moving up basically means, again I am repeating, sorry for that, the inputs remain fixed, output increases, horizontal movement onto the left means output remains fixed, input decreases. And then if I consider any movement in the tangential direction, so this angle is actually 90 degrees. So, obviously it would move in this direction 90 degrees, which would mean that there is a proportional increase in the output and proportional decrease in the input. So, if this moves in this, consider this is 90 degrees for the time being, I do not want to clutter it too much. So, this is the increase in the output and this is the decrease in the input. So, this is decrease in input and this is increase in output. And similarly, when you have the output along the x axis and input along the y axis, you can basically formulate the problem in the similar way. And in the case if you have the variable return to scale, you have it can be again done where you have different input along the x axis or input along the y axis. I have only taken input along the y axis. Then you can have different direction of movement depending on the variable returns. It can either move vertically up or down depending on whether you have been able to draw the output along the y axis. So, here output is along the x axis. So, the curve is in the other way around downward. And then you will obviously have the vertical lines left or right, which is blue in color, would remain same. In the case output is along the y axis. So, but the pink line would be moving vertically up, not down as in this diagram, and the radial movement would be happening onto the northwest corner method or onto the right corner method, depending on which direction you are moving, considering that you want to basically proportionally decrease the input and proportionally increase the output. And there obviously you can formulate the same, find out the same way that depending on the input oriented model or the output oriented model or both can be changed, you can basically find out in what proportions the input and output would change to make it efficient, the DMU is efficient. Now, having said that, we have been talking about the drawing the diagrams, but till now for in the first 38 in the first class of the 8th week and this is the second class of the 8th week, I have been telling about that we can formulate in optimization problem, we can solve it, but I have not come into that. So, here what I am going to do now. Now, there would be two different ways of trying to handle the problem. One is the output oriented model, where your main concern is to do with the output, and another the input oriented model, where your main concern will be something to do with the input. So, how you look at the picture would basically change the formulation of the problem, but the general crux of the matter, how you solve it, remains the same. Now, if you remember, we have taken x and u are the corresponding decision variable and the weights for the inputs or input bundles, and the suffix for I and k, I is from 1 to m, k small k is equal to 1 to capital K, while the corresponding decision variables and the weights for the output bundles are y and u. So, again their suffix are j and k, j changes from 1 to n, capital N, which is the number of outputs, while m I am again repeating is the number of inputs, while k changes from 1 to capital K, well k is the number of DMUs. Now, if you see this ratio, what does the ratio mean? The ratio means that I am trying to basically find out a maximization of a ratio, where the ratio actually means the efficiency. So, in the denominator you have basically in the numerator and denominator, in the top part of the numerator you will basically have the total bundle of all the output, that means what is coming out, because that you are summing up by multiplying the decision variables with the weights, and in the denominator. So, numerator basically has the total bundle of output, and the denominator you have the total bundle of inputs. So, what you are trying to do is you are trying to find out that what is the ratio, considering you want to maximize it. So, higher the ratio is, and obviously in the highest case it will be 1, then in that case the efficiency of that DMU, considering that k is equal to 1, 2, 3, 4 till capital K is 1, that means its actual efficiency is 1. Now, you want to maximize the efficiency, and you will do it for each and every k values, k is equal to 1, 2, 3, 4 till capital K. But in that case, when you are trying to maximize the efficiency or the ratio, you will have some constraints. These constraints are actually the constraints corresponding to all the rest of the DMUs. So, say for example, if I am trying to maximize the efficiency of the first DMU, I will basically keep the constraints of the first along with the second to the kth one. When I am trying to basically maximize the efficiency of the second, I will keep the constraint corresponding to the first, second, third till the kth one. When I try to basically maximize the third one, I will keep the constraint corresponding to first, second, third till the kth one, till the last optimization problem which you will have is basically trying to maximize the ratio corresponding to the capital Kth one, and the constraints would be corresponding to the first, second, third till the capital Kth one. Which means that if I have 10 DMUs, I will have basically 10 such optimization problem. Now, the optimization problem looks like it is basically a ratio, which means it is non-linear. Well, I agree with that, but we will slowly convert this problem from a non-linear one into linear one. So, first let us pay attention to the constraints. Now, what are the constraints? Now, if I am trying to maximize the efficiency, which would mean that I would try to increase the efficiency of any kth one, any arbitrary kth one, k can be 1, 2, 3, 4 till the capital K one, corresponding to the fact that the ratios of all the rest 1 to capital K are all less than equal to 0, less than equal to 1, sorry, which means that any one can increase, but the constraining fact would be none can be more than 1. So, obviously, maximum value of each of the efficiency for each of this capital K number of DMUs would be maximum is equal to 1, or in the practical sense it will be less than equal to 1. So, what I will have is for K is equal to 1, which is the first DMU, I will have the bundle of outputs divided by the bundle of inputs is less than equal to 1. Similarly, I will have a second constraint where in the numerator I will have the summation of the bundle of output for the second DMU divided by the bundle of inputs for the second DMU also is equal to less than equal to 1. The third constraint would be in the ratio, the top part or the numerator would basically be the bundle of all the outputs corresponding to the third DMU, and in the denominator you will have basically the bundle of inputs for the third DMU, and we will continue doing that till we reach the kth one, where the kth one is shown here, where in the numerator we have the bundle of outputs corresponding to the capital Kth one. So, say for example, I said that if there are 10 DMUs, it will be corresponding to the 10th DMU bundle of outputs, and in the denominator you will basically have the summation of the all the bundle of inputs for the kth or the 10th DMU, and all of them would be less than equal to 1. And in this case, obviously it will mean that all the values of weights u I k, v I k, and obviously the variables which you are considering would definitely be greater than equal to 0. Now, this is the problem formulation, and we have such k number of DMUs where k is 10. Now, if you see, the problem is a nonlinear one, maximization of a ratio, and the constraints are also nonlinear because they are a ratio less than equal to 1. Now, what I will do is that for the output oriented model, I will basically as per the concept, I will basically tweak it a little bit and convert into a very simple linear programming. So, here it happens. Now, watch carefully, the maximization was a ratio, now the maximization will be only on one term. So, I am going to basically convert the denominator which is there in the objective function and keep it normalized and fixed at 1. If I keep it at 1, maximizing the ratio would also mean that if I am basically keeping the denominator fixed at 1, I can maximize the numerator also. So, they would basically mean the same thing, in the sense the constraints would also change accordingly. So, what I have, I am basically maximizing the numerator, which is the bundle of outputs, but as I am doing that, I am converting each and every constraints along with the fact that I am adding an extra k plus 1th constraint, which is corresponding to the denominator which is being removed from the objective function and being brought into the constraint. So, where it is, let me check. So, this had, so in this problem actually this was the ratio divided by a summation of I is equal to 1 to capital M u I k x I k. So, this was the bundle of inputs. So, this part is removed here. That means, I am added the kth plus 1 constraint. As I am basically forcing the denominator to be 1, hence I force it to be 1 and try to basically maximize the numerator, which I am doing. Now, as I am doing it, the constraint will also be changed in a very simple way. The initial constraint for the first one was what? The bundle of outputs for the first DMU divided with the bundle of inputs for the first DMU was less than equal to 1. So, when I basically take the input onto the right hand side and then again bring it back to the left hand side, the equation now becomes like this for each and every constraint. The bundle of outputs, the bundle of inputs. So, there is a minus sign here and less than equal to 0 because I am considering the efficiency less than equal to 1. Similarly, in the second constraint, it will be bundle of outputs minus the bundle of inputs is less than equal to 0. Similarly, for the third one, bundle of outputs minus the bundle of inputs is less than equal to 0. I continue till I reach the kth one, which is the bundle of outputs for the kth DMU, which is the 10th one, minus the bundle of inputs for the kth one is less than equal to 0. And this one, which I have already discussed, the denominator from the objective function has now come into the constraint, such that for now for the optimization problem I have converted that in from a ratio 1 to a maximization of a linear function, because this is a linear function. The constraints are already converted into linear one, because the ratios of less than equal to 1 has been converted into sum part minus sum part, bundle of outputs minus bundle of inputs is less than equal to 0 for each and every of this k or the 10th DMU, 10 number of DMUs, and the 11th one constraint is basically the bundle of input which is coming from the objective function. So, if we had 10 such DMUs, initially we had the ratio maximization of the ratios of 10 DMUs, corresponding to the fact for each of them the constraints were the same. So, that means there were 10 such constraints. Once it is converted, now we have an objective function which is a maximization of a linear function. For all 10 there are different objective functions, and obviously it was different in the initial case also. Now, in the second conversion we have maximization of the bundle of outputs for each and every DMU. The constraints 10 in number are exactly the same, bundle of outputs minus bundle of inputs is less than equal to 0, and each of the 10 objective functions, now we will have the 11th one which are different. The first one will be the corresponding to the bundle of inputs for the first one, the 11th one for the second objective function will be the bundle of inputs for the second DMU. So, and henceforth till the last one which is the 10th optimization problem, the 11th constraint would basically be the constraint corresponding to the fact that it is the bundle of inputs for the 10th one is equal to 1. So, in each of these they are 1, and once you see the problem, it is a very simple optimization problem which can be solved in the using the concept of linear programming, and you can get the answer using the corner point solution, where you basically finalize the tableau, then considering the, and obviously if they are less than type, you will add the, or greater than type, depending on the minus and plus sign whether they are, you can basically add the slack and surplus, and also basically use the concept of artificial variables if required. I am just giving you the background, and then we solve the problem and get the values of the decision variables as required. So, with this I will end this the second lecture in the 8th week and continue more discussion about the input oriented model for the DA, and then go into the other concept of integer programming. Have a nice day and thank you very much.